Dear students, this is perfect gas equation. P is pressure, V is volume, R is universal gas constant, T is Kelvin temperature, and mu number of moles. So now here mu is a constant, R is also a constant. If you take T also constant, that is at constant temperature, if you take this also constant, then what happens? The product of P and V becomes a constant. Or V is equal to constant by P, or V inversely proportional to P. So at constant temperature, volume of a gas is inversely proportional to pressure, and this is known as Boyle's law. Here the pressure is P and volume is V. When the pressure was doubled, volume decreased to half. This is Boyle's law. And we can draw a graph also between the two variables. So this is the graph. On x-axis we have taken volume. On y-axis we have taken pressure. See how the graph is. At temperature T1, the graph is like this. As say, if you move from down to upwards along y-axis, pressure is increasing. So when the pressure is lower, the volume, so for example, for 0.4, see the volume is this much. So as the pressure is being increased, the volume is getting decreased. And this is for this is at temperature T1, and this curve is at temperature T2, and this curve is at temperature T3, and the three temperatures are in the descending order. This is a perfect gas equation. P means pressure, V means volume, T means temperature, and these two are constants. Mu stands for number of moles, R constant for universal gas equation. So perfect gas equation is a relation between three variables: pressure, volume and temperature. Previously we have considered Boyle's law, and the Boyle's law deals with two variables P and V at constant temperature. At constant temperature, the relation between P and V was studied by Boyle's law. Now, out of the three variables, if suppose P is kept constant, here T was held constant, and relation between P and V was studied by Boyle. Now let us keep P constant. And let us study the relationship between V and D. So if P is held constant, let us move P to right hand side. Mu, R and P, now the three are constants. So here V is variable, here temperature is variable. So this, since this is a constant, you can take this as a constant of proportionality, and you can write that this suggests you that V is directly proportional to T. V is directly proportional to T. And this is known as Charles' law. This is known as Charles' law. And this Charles' law is shown graphically here. On x-axis, volume of the gas taken, on y-axis, Kelvin temperature taken, and for at a constant pressure P1, we got a straight line here, because these two, V is directly proportional to T. When there is direct proportionality between x coordinate and y coordinates, then we get a straight line. So at pressure P1 we got this line, at pressure P2 we got this line, at pressure P3 we got this line, and P1, P2, P3 are in the descending order. Dear students, let us take a mixture of three different gases: 500 milliliters of nitrogen gas, 300 milliliters of oxygen, 200 milliliters of carbon dioxide. So all the three are mixed to make 1000 milliliters, that is 1 liter. And now you know very well that under normal temperature and pressure conditions, 22.4 liters of any gas will have 1 mole of substance in it. 22.4 liters means 22,400 milliliters will have 1 mole substance. Here you have taken nitrogen gas 500 ml. So in 500 ml of nitrogen gas, how many moles will be there? I have calculated. I got 0.022 moles. For 300 ml of oxygen, I got 0.013 moles. For 200 moles of carbon dioxide, I got 0.009 moles. So in this way, I calculated the moles of substance taken. Let me write the perfect gas equation for this mixture. Here in place of mu, I have taken three different gases, therefore I should write now the pressure exerted by the gas mixture. So making P subject, taking this V that side. Here V is 1 liter, and substituting the values, theoretically also we can calculate the pressure exerted by the gas mixture, and experimentally using manometer also we can find the pressure exerted by the 1 liter gas mixture. Now mathematically let us expand this. Now all the three terms represents again pressure only. If you consider this term is having mu1. What is mu1? Mu1 is the amount of substance present in 500 ml of nitrogen gas. Okay. R is universal gas constant, T is temperature, and V is volume, and here V is 1 liter volume. Here also 1 liter, here also 1 liter. But here mu1 is number of moles of nitrogen gas present in 500 milliliters. No? Yes. Here mu1 value is of 500 moles of nitrogen gas. Here mu2 value is of 300 ml of oxygen. And here mu3 value is of 200 moles. But in the denominator you are taking 1 liter volume. So how? So now see, this term represents the pressure, no? So if you now you are going to calculate pressure exerted by nitrogen gas, but you are taking 1 liter volume. So what all you have to do is, as far as you are allowed to take only mu1 moles of nitrogen gas, you are allowed to take only 0.022 moles of nitrogen gas. So you transfer the same amount of 500 ml of nitrogen gas into manometer. But there in that manometer the container is having 1 liter capacity. That manometer is having 1 liter capacity. So when you transfer 500 ml of nitrogen gas, this 0.022 moles of nitrogen gas into this 1 liter chamber, immediately see, gas has a behavior. It occupies as much volume available as. It has no fixed volume. If you give it a space of 1 liter volume, it will occupy 1 liter volume. But the substance in it is 0.022 moles only. So 0.022 moles of nitrogen gas occupies 1 liter volume here. When you are measuring its pressure using a manometer, the manometer chamber is having 1 liter volume. So when you send 0.022 moles of nitrogen gas into manometer chamber, there it occupies 1 liter volume, and there it is allowed to there the manometer measures the pressure exerted by the nitrogen gas. So the substance is 0.022 moles only, but the volume occupied is 1 liter. So under these conditions, the pressure exerted by the nitrogen gas is, say, P1. Similarly, for oxygen gas, P2. Similarly, for carbon dioxide gas, P3. So, and here, mixture. Here, mixture. So, first let us do theoretically, afterwards experimentally. You take this term, mu1 0.022 or universal gas constant 8.3, T room temperature, V volume 1 liter. Substitute all the values, you get certain value. Here mu2 0.013 moles or T same, V 1 liter. Substitute, you get certain value. Next mu3 0.009 moles or TV, same values. Substitute and you get a value, P3 value here. And you add the three values. You get some theoretical value, P. Now, using manometer, you are calculating. You get the experimental values. In this way, you find theoretical values and experimental values. They will be same. Similarly, adding the three experimental values, you get here p value. Here also theoretical value and experimental value will be matching. Since this was experimentally also verified, this has become a law, and this law was proposed by Dalton. Therefore, it is known as Dalton's law of partial pressures. The statement of the law is the total pressure of a mixture of ideal gases is the sum of its partial pressures.